this guiding is made in one part of the genome that guides the Cas9, which is a generic activator for a particular target in the TPAM promoter. And so here's the NAD ratio, NADH ratio of 7.5. We can look at this in the context of this in the context of other regulators or other metabolic regulators of this phenomenon. And again, we can see this huge impact of NAD to NADH ratio. So we also can measure the impact on mitochondrial mass, which again is dependent on the guide RNA, as we can see here, and is also has minimal effect on the reactive oxygen species. So I just want to thank in particular here Margot Monroe and Bobby Padua, who are postdocs in the lab that have really initiated this particular study. John Ock, who has been instrumental not only in running the lab, but in computational biology and design of the CRISPR-Cas9 guide RNA. So some of the software for this is available on our website. And many people around the world are using it to design their guide RNAs and CRISPR analyses. So I left more than enough time for questions, so please, hopefully that provokes you. Thank you. Many people will be thankful in institutions as well. This is my conflict of interest slide. And we will be talking about bio-nanotech and comparing it to many other technologies. So from today and yesterday, one gets the impression that this is not really an audience. This is more like a congregation. We're talking about the Church of Testable Hypotheses. So if you'll open your hymnal to page 241, there is this chart of augmentation, past and current, where we clearly are no longer natural species. We go much faster in many ways. We've extended our senses and our abilities. And in particular, our memory extends more than just a few minutes in some animals to an entire lifetime, to thousands of years, and all of written human knowledge available. But there are perils to the kind of exponential extrapolation that many of us here are addicted. This is two curves, actually. It's both the electronics industry, the Moore's law, and dotted lines. And the green curve is the molecular and genomics curve. It was predicted that it would take about 6 decades, going on a very aggressive Moore's law type of exponential, to get to an affordable human genome for the $3 billion that I helped initiate in 1984. It could have flatlined when the Genome Project money disappeared. And the lesson that I'm taking is not so much that it's hard to predict the future. It's more about how do we connect the dots, not just how do we predict the dots, but how do we actually bring these exponentials to occur. Unfortunately, this curve did not flatline, as you've seen in one of Ray's slides. It accelerated, and instead of 6 decades, it arrived in 6 years. So I may be one of the few people on the planet that calls Ray Kurzweil a pessimist. And furthermore, I mean, there's a tendency for us to put great faith in electronics. Ray correctly mentioned molecular as the next wave for possibly replacing electronics. We need to get down to smaller and smaller features, and that's where molecules come in. And as part of this revolution, I'm going to show you 2 slides where these are not where the molecular technology is already 6 logs ahead of the electronics. And as you can see from that previous slide, it's accelerating. It's going much faster than Moore's law, 10-fold per year on occasion, many years in a row, rather than 1.5-fold. And here's an example where the density is higher. In the next slide, I'll show you where the energy efficiency is 6 logs higher. And here we took a book, the Regenesis book, and encoded it into digital DNA. And this was about 6 logs better than any of the commercially available consumer storage devices, including flash memory and disk drives and so forth. And that's density. And you can see me down there in the lower left, actually putting on gloves and doing experiments. That's the fun part of molecular, as you can still do it. Now, this is a progress curve for energy efficiency. And you can see we are making progress at roughly the same rate that we're making progress on density of large-scale integrated circuits. But still, there is more than a million-fold gap between what the best energy efficiency is for these circuits and the already high efficiency of molecular devices. You can call these nanorobots, if you will, but these molecular devices like DNA polymerases. And I'll show you a couple of examples of what we can do with these molecular machines like DNA polymerases in just a moment. But keep this in mind that we're 6 logs at least ahead, and it's going faster. And here's an example of a molecular computer. Exactly what this person looks like is not quite so relevant as what he did with a molecular computer inside of his brain. And it's not quite so important what he did in such a short period of time. Speed was not the issue. It was the qualitative nature of what he did. This was a huge number of completely paradigm-changing physics papers were written, 5 papers in a little over half a year. And the 2 bell curves there represent that clearly in some regards he is off way on the edge of the bell curve in certain computational senses, human computation. What if he were in the middle of the bell curve, if there were a new bell curve made up of human beings, or molecular computers, if you will, where he was average? What would the extreme look like in that case? It's a very interesting thing to reflect on. And you can see the Jeopardy computer, Watson, is nowhere near this particular individual. And it may be qualitatively different rather than merely being able to remember more. I mean, the fact Einstein did not have access to 200 million web pages, but he still did a pretty good job as a 26-year-old. When we look for exceptional individuals, it's not just about computing our ability to think. It's also our ability to live a long time, because it takes us long time to accumulate these important memories. Here are some individuals, and you shouldn't take home from the slide that the way to live over 110 years is to smoke and drink. But the point is that you can, despite, no matter what the environment is, no matter how many infectious agents they've been exposed to, and other risks that epidemiologists tell all humans reveal, they have potentially protective genetic and environmental components, and we need to define these, and we want to be able to share this information and possibly as therapeutics. Now, those supercentenarians and centenarians that are over 100 or 110 years old are being sequenced right as we speak. We don't yet know what rare protective alleles they may have, but we do have some examples of rare protective alleles that are already understood in some detail already. For example, myostatin in STN double nulls, meaning knocking out low copies of what would be from your mother and your father, results in people with very large lean muscle mass and very low probability of atherosclerosis. These are very rare. Maybe a handful of people on the planet are known to have this, and they're healthy as far as I know in every other regard. LRP5, if you've ever seen Bruce Willis in Unbreakable, that's actually based on some rare individuals that have this heterozygous state where they are have extremely unbreakable bones. They are 8 standard deviations out in bone density. PCSK9 is a mutation that's inspired the drug industry to develop a new type of anti-coronary artery disease, because these individuals have such incredibly low levels of bad LDL cholesterol that some physiologists were surprised that they were alive. And on the contrary, they had extremely low coronary artery disease. CCR5 will get its own slide, but double nulls in CCR5 and double nulls in FET2 are resistant to some very serious viruses, HIV and norovirus, for example. And APP is, certain versions of APP push you at risk for Alzheimer's, but the reason it's on the slide is there's certain versions that make you can delay Alzheimer's by a factor of 10 to 15 years. So all of these are rare protective alleles. They're not the rare deleterious alleles that we normally hear about in genetics. Now, we selectively breed organisms like dogs. There could be 1,000-fold difference in the weight of adult dogs. We also selectively bred ourselves, and so there's big parts of the world that we're malaria resistant, so we have persistence of the enzyme that allows us to train milk well into our adulthood. These are selectively bred, somewhat natural. They're genetically engineered organisms as well, like these glowfish. And Timothy Brown is one of the first genetically engineered human beings. He got a stem cell transplant for the CCR5, which is the receptor for the AIDS virus. And having he had the unfortunate situation of being both having leukemia and HIV. Treating his leukemia resulted in this treatment for AIDS, which is now generalized in that somewhat serendipitous situation to a molecular machine called zinc finger nuclease that will go in and target both copies of your CCR5 gene, so that your T cells, the cells that the HIV virus normally infects in your immune system, don't have the HIV receptor, and so they selectively survive this, and you become cured. Not something that multi-drug resistance and vaccine trials in HIV have not proven quite as effective as we hope. But this is something where you literally remove the receptor. This is in phase 2 clinical trials. This tells us pretty far along, and it is curing AIDS patients. And it's interesting in that not only is it more precise than any previous gene therapy, but it's aimed at an assertion of augmentation. It's not curing some rare disease, rare deleterious thing like cystic fibrosis, sickle cell. It's aimed at all of us in a certain sense are susceptible to the AIDS virus and other viruses. The next step in this is CRISPR. I'm not going to spend a lot of time on this, but listen, it's like, in the graduate plastics, remember the word CRISPR? Okay. It's another way of doing this. It's about 100 times easier and about 10 times more efficient than the method that's already in phase 2 clinical trials. So this is going to allow human genome engineering on an unprecedented scale. We can also make tissues. This is an example where in a mere 4 days we can take human skin-derived stem cells, which is actually from my skin, that's turned into embryonic-like cells. They're adult-derived, and then they're turned into these bipolar-like neurons using going through an irregular pathway. Now, I should mention that those stem cells are derived from the Personal Genome Project. This is the world's only open access source for genomes, environments, and trait data, but not just data, interpretation software, and these cell lines. These cell lines are broadly distributed internationally. The NIST, National Institute of Standard Technology, and the Food and Drug Administration have had a unique new collaboration to produce standards in this field called Genome in a Bottle. And you can go to genomeinaBottle.org to learn more about this. And they looked over the world for suitable samples, genomes, and cells, and they found that this Personal Genome Project was the only one that was properly consenting individuals for this kind of open project where you could share it and make international standards. This is an example of the annual meeting we have where the Personal Genome Project volunteers, I know many of you in the audience are in this, they're invited to come, and unlike most medical settings where anonymity is promised but not necessarily delivered, here they can wear name tags and say, hi, I'm PGT. And it produces a much more participatory environment where people can share their information. And so this is genomes, environments, and traits. An example of a trait that's relevant to this conversation is functional magnetic resonance imaging. It's unfortunately a low resolution, but it is whole brain and it is functional. It tells you it gives you information about what you're thinking in a way that you don't get from any other methods. And here's an example of one of the PTP volunteers in the previous slide with an MRI scan. And you might worry that these are virtual slices, not actual slices. This is my brain, so thankfully they are virtual slices. These are cartoons of actual slices of the mouse brain, which is part of the Allen Brain Atlas project. In this project, unfortunately, they wanted to visualize all of the molecular identification of all the cells in the brain, but they can only do one at a time, so they have to do thousands of brains, each one getting one at a time, and then try to integrate that data. But each brain is a unique story, and so that they don't really align that well. It's still a useful atlas, but wouldn't it be great if you could do these thousands of different molecular IDs or RNAs in a single brain, and that way they're integrated. Every voxel, every pixel of every section can be aligned and know where you are. And not just for the RNAs and other molecular identifiers, but what the brain was thinking during the activity, and we'll get to that in just a moment here. There are hundreds of thousands of individuals in the world who have electrodes implanted in their brain already. So this brain initiative that we're embarked on that Obama helps get going is already in the clinics. This is the case of an epileptic who also contributed to experiments. In this case, on the top of the slide, you see they happen to, with a small number of electrodes, this is the one that Ed just described, they happen to find, by showing lots and lots of images, one neuron that, of course, were one set of neurons that corresponded to Jennifer Aniston images and not any other images in the control down below. Now, this is simultaneously very inspiring and very frustrating in the sense that we now know that there's a very high-level one, not the lower-level ones that we've been talking about so far today, but a very high-level cognition going on here. But it's frustrating we don't know how many other neurons are involved, what other images would produce, and how the whole thing fits together. For that, we really need to measure every neuron and at appropriate speeds and long periods of time. And that's what the Brain Initiative is about. It's not just about measuring them, it's also about stimulating them, because we need, as Ted mentioned, we need to be able to deal with pathological situations, and we need inevitably to augment our capabilities of helping individuals. Here's this long list, similar to the one that Ed showed. And John Donahue's group has helped this woman who was tetraplegic for a decade to now move a robotic arm, and John and his colleagues hope to now make it so that she can move her own arm and at high speed and much less awkwardness than currently is possible. This is from Ed Boyden and his co-workers that he just showed you, where you can have arrays, but these arrays are not at the density of measuring all 80 billion neurons in the human brain, or roughly 1,000 of that number in the mouse brain. To do that, we want to leverage many different methods, including ones I just showed, but in particular the molecular ones that allow you to do this. Remember, the high density and the high energy efficiency. Energy efficiency, this is not about saving, controlling, or retrieve. This is about the amount of energy that you can allow to transact in a brain. A factor of a million is a big deal because the brain only has 20 watts of energy dissipation, so a million times that would not be a good thing. Here's an example with where one can look at the in situ, so sequencing, we normally take it out of context and sequence it, but here you can do it in situ, and so you can learn about RNAs, other molecular identifiers in great detail, and we have on the order of, we're not limited to the number of colors because we reuse these colors in this new method called fluorescent in situ sequencing, so you get effectively 4 to the 60th power of colors, and this is really no different from next-gen sequencing except that it's in situ. And here's some examples of some human cells where we look at all the RNAs, and we're seeing all 4 colors at a particular cycle, and if you look at a particular place in a particular messenger RNA in each of these single-straight cells, you can see 1 color. We can, the next generation of sequencing devices may well be these molecularly molecular electronics hybrids with so-called nanopore sequencing, where we have DNA polymerase that helps couple to ion channels, and you basically convert DNA information into ionic information into computer information. So it's going from DNA to ions, but for the brain, we're interested in the opposite, going from ions to DNA. And we now have molecular nano devices that can do this. They can go from light to DNA, and they can go from ATP, other small molecules of DNA, so ions to DNA. And these are some of the graduate students and postdocs involved in this project. Ions to DNA, we have the ion channels that are going through the spiking, or in some cases, non-spiking behavior that Ted talked and Ed talked about. But here is influencing the fidelity of the DNA polymerase so that the time series of the calcium, say, turns into a spatial series of changes in the DNA sequence, which you can then later read out or compute on. This is, again, a million times denser and a million times higher energy efficiency, so it fits in the brain. Here's some data taken from a much older paper showing the effects of calcium sort of in the micromolar range, which is physiological. And we're extending this to new polymerases. And we're, as part of the Brain Initiative, thinking about the Rosetta Brain, where we're not picking one particular winning technology. We're trying to stimulate new innovative technologies and to integrate them all into one brain and do that over and over again in different brains, in different pathological settings, in humans and other organisms. And here's a laundry list of the types of bytes that we need to store this information. If you're interested in brain uploading and downloading, these are the kind of absolute minimum numbers that you need to be considering. But it's not out of range. It's not necessarily far off in the future. So we're done. Just in summary, we already augment ourselves extensively, get used to it. Extrapolation can be off by 5 decades or more, either in the positive or in the negative direction. molecular technology is probably where we're going with electronics, and it's already here. Again, it's 6 logs better, and it's improving faster in certain cases. Remember the word CRISPR, even though I haven't properly explained it. And innovative neurotechnologies is part of the acronym BRAIN that Obama has gotten us all thinking about. And it's about a plurality of technologies, including, but not limited to, the polymerase technologies and the fluorescent CT sequencing I just talked about.
Please join me in welcoming Dr. George Church.
Thank you very much. I will be making some forward-looking statements. Says futures in the title of my talk. It doesn't necessarily mean I'm advocating them or that I am optimistic. It means that in order to do engineering long-term planning, you need to think about, and cautionary tales are in order. Like building a cathedral, you might have to plan a century in advance. This is my conflict of interest slide. I'm highly conflicted. But it's also this set of institutions, both nonprofit and for-profit, that help us bring our technology into reality, into daily life. These are some of the topics, we'll talk mainly the top 3, which is this idea of synthetic versus natural prediction, and where we stand in terms of human genome engineering. We have a love affair with the idea of the natural, even though we as a species are about as unnatural as you can imagine. We have, I'll mention 4 diseases. There are diabetes and heart disease, to which we succumb due to natural compounds such as sucrose and cholesterol. And the source of carcinogens are robust in nature. We get on the order of 1,500 milligrams a day of plant toxins and pesticides that are listed as rodent carcinogens. Such the cancer side and the infectious disease side is there are many instances where infectious agents are spread through vegetables and meats. We have a huge difference of intention and obsession with the risks. The risks of genetically modified foods are not well documented. The risks of driving a car are very well documented, 1.2 million deaths a year. My laboratory and my obsession is about safety and building engineering. Safety is not just a matter of saying we want the world to be safer. We have to create technology. And here's some of the technologies that we use for automobiles. It doesn't sound like we've done our job entirely if there's still 1.2 million deaths a year, but these are the sort of things that inspire us to do better in a variety of engineering fields, including genome engineering, which is what we're talking about here. We have standards of testing in biology. Increasingly, we have these redundant systems in isolation that we're using, physical, genetic, and metabolic. I have advocated that we do extensive education licensing and surveillance since 2004, in particular in the field of synthetic biology, since the technology is getting exponentially less expensive, more able to engage the public through do-it-yourself biology. I felt then and feel now that we need to have better and better tools for tracking the dissemination of the information, the chemicals, and the instruments. Here's just a snapshot from the trenches in the laboratory. We're trying to address what it is that people want when they say that they want organisms, genetically engineered organisms that do not spread in the wild. This is one of the many critiques of genetically modified organisms. And this is one attempt that we've recently published where we make them genetically isolated, metabolically isolated, even if they, whether or not they're physically isolated from the environment, they cannot exchange genetic material successfully. So, let's talk about prediction. These were forward-looking statements where New York Times, nothing against New York Times, maybe, but back in 1903, they made the modest prediction that it would be 1 to 10 million years, a nice broad range for a flying machine. And even Wilbur Wright, who was much closer to the events than the New York Times, perhaps, was off by about 48 years in his estimate. And so we make such mistakes, and even within my field, my fields of computing and biology, we have these 2 trend lines, sometimes called Moore's Law. It's not really a law, it's a trend. It could deviate from this line at any point. The blue line was various biological things, the sequencing and synthesis, reading and writing DNA. It followed the electronics Moore's Law line at about 1.5 volt per year for many years, and so it seemed like, wow, this must really be a law. This covers general biology and electronics. But then we blew it, and we went way off the reservation, and it took about 6 decades to bring us down to a 4-year-old genome, or more like 6 years. So we're down around $1,000 cost. We don't yet have $1,000 that you can go out and individually get genomes, but it's at bulk rate. That's where we are right now, which I think is cost effective today for a variety of things. Kevin Kelly documented how long it takes for new technologies in general, this includes Crossroads and so forth, to be banned, and then the bans to be released. It's almost inevitable that technologies like, really dangerous technologies like railroads and automobiles would be controversial. But the time that it's taking before they become uncontroversial is shrinking. This isn't to say that we